Welcome back. I'm Steve Miller. I'm a math professor at Williams College, and these are the coronavirus math lectures sponsored in part by the Journal of Number Theory and the Teachers of Scholars program. Today we're finally going to get to some applications about why we might care about quadratic equations. What can we do with them? And again, all of these lectures are available online. They can come from my homepage over here. That's an underscore with the public. Okay. So the application we're going to do today is trajectories. So there's a lot of different things we can look at. It was supposed to be cannonballs, but that doesn't actually look like a cannonball. That looks like a person. But you can shoot whatever you want out of a cannon. It's a question of whether or not you will get into trouble. So we've got cannonballs. We have water fountains. In the old days, you could actually go to a water fountain and touch it in public and get water out of it and drink it. We have fountains, and we have flights of baseballs. And I want to talk about the paths they take and how you might compute them, how you can use this to solve some problems you might care about. All right, so let's consider a cannonball or a batted baseball. So here is a really nice picture about the path. It turns out that if you assume that there's no air resistance, the path is given by a parabola. So that means if x is time, then f of x, where is it, is going to be given by ax squared plus bx plus c. Or maybe not time. Time is not necessarily the right thing to be doing here. Sorry. Let's say this is going to tell us its path. It's going to have a nice parabolic shape. Now, when you look at this, is this a parabola that's pointing up or pointing down?
Huh? Right.
Well, when you think of the parabola x squared.
No, what do you mean by up? Like the like?
So let me quickly.
Oh, I guess down.
So it's going to be down. So let me quickly go to. And so what we can do is we can share a screen. And so if I come over here and do a freeform, this would be like an up parabola.
Okay.
And this would, right,
would be
exactly. And so,
I just got confused.
right, so if you haven't seen the notation, it's a little hard. So for this one, this would be an up parabola. And that, would that be a y equals x squared or negative x squared?
Negative? Wait.
So as x is getting very large, is it going to positive infinity or to negative
positive,
infinity?
so y equals x squared.
So it would be y equals x. Note as x goes to infinity or minus infinity. Down here, this is the down. So it would be y equals
Negative x.
Negative x squared. And we have a similar thing about what happens. All right, so returning to the slides. Here's a nice picture of the shape. It does look like a parabola. Now, we've seen that there's more than one way to write a parabola. So I just learned from your math teacher today that the version we're doing ax minus h squared plus d, that's called vertex form. And that was more convenient for solving, and so that might also be more convenient for other things. We saw it was also really good for plotting. So let's consider a simple case. Again, constant force of gravity, no air friction, and we are going to fire straight up. Now, should we be firing a cannonball straight up or a baseball?
Baseball?
A baseball. If you fire a cannonball straight up and it comes back down, this is not good.
No.
Even if you catch it, it's not good. Whereas a baseball is not so bad.
Yeah, it'll hurt.
All right.
It will hurt.
It will hurt. But of course,
right,
we can of course do this theoretically. And let's imagine we throw or fire a cannonball up at 488 meters per second, and we start off at 10 meters. Okay? And then at time t, physics, and this is, we're not going to do physics, physics gives us the following formula for a cannonball's height as a function of time t. It's 10 plus 488t minus 4.9 t squared. And we've plotted this up over here. So when you look at this, approximately where does it look like the cannonball will hit the ground?
100 seconds.
100. Is it at 100 or is it a little bit before, a little bit after?
Looks like it might be a little bit.
Slightly before. Where do you think the maximum height is? around
before
1.
50?
Yeah, and if you look at it really carefully, you see how the maximum height is about 12,000 meters? Does the
Yeah.
fact that it started off at 10 meters make much of a difference?
No.
No. And so in fact, when it hits 0 or 10 meters, it's really about the same. And so what do you notice about 50 and 100? What kind of relationship is that?
100 is like 0, and 50 is practically. 100 is the end, and 50 is like right in the middle.
Yeah, 50 is right in the middle. So I wonder if the maximum point occurs when half the time is half the time is up, half the time is down. And then their resistance could be very different.
Yeah.
So the first question is, can you find the highest point?
Yeah.
Well, you can approximate this, but can you look at this and can you give me the value of t that makes this largest? It's not so clear looking at this. Now, if you know calculus, you can look at the derivative, which gives you the rate of change, and you could use that, but even though we did calculus in an earlier lecture, we're not going to use that today. Maybe we could write this polynomial, this quadratic, in a better way. And so if we write it as a t minus h squared plus d, do you think a is going to be positive or negative?
Positive.
So if a is positive, what happens as t gets larger and larger and larger? Well, t minus h squared, what kind of quantity is this?
T minus h squared.
Yeah.
Square.
Well, when we square a number, what can you say about t minus h squared? What kind of number is it?
Positive.
Or it could be.
I.
No, it could be positive, but what else could it be?
Negative.
So could t minus h squared ever be negative?
No.
No, but
it could be 0.
It could be 0, so it's non-negative. So when you look at this, as t gets very, very large, is the cannonball going to keep going higher and higher and higher?
Yeah.
Forever.
No.
And eventually, if we could imagine it could keep going into the earth, it would be going down, down, down. But if a was positive, then as time passes, it would just keep going higher and higher and higher. So a should be negative. So just looking at this, we see that a should be negative. And what do you think the largest value of this would be? Since a is negative, what would you want t minus h squared to be?
2a.
But because a is negative, what would be
greater than?
Well, I'm saying, what t could we choose to make this as small as possible? A is negative, right? I'm sorry, to make this as large as possible.
Infinitive?
No. We have a times t minus h squared, right? So let's say a is negative 4.9. The larger t minus h squared is, the smaller this height is going to be. We want this height to be as large as possible. So what should we have t minus h squared be?
Like a minus 1.
Well, if it's a minus 1,
or like negative 1.
Well, t minus h squared, you just told me it's non-negative. It's either 0 or positive.
Yeah.
Which would you want it to be? Do you want it to be 0 or do you want it to be positive?
0.
Because if it was positive, you would have positive times negative is?
Negative.
And then that would make things smaller. So what value of t would make this contribution the smallest possible?
When t minus h squared equals 0.
And so when does t minus h squared equal 0? When t equals?
0.
So when would t minus h squared equal 0?
When t minus h equals a, like
No.
the opposite of a?
No. You want t minus h
squared
to be 0.
When t minus h squared.
So if t minus, no, you said you want t minus h squared to be 0, right? So let's think, when is t minus h squared equal to 0? We can go back to sheet over here. Read all of this. So we're trying to solve minus h squared was 0. So what else must you, what do you know?
That everything has to be.
So think, what is
it? T minus h has to be 0.
So t minus h has to be 0. All right, well, if t minus h equals 0, what does t equal? H. So that would be the solution. Right? Yeah. So if we want that to be 0, we would have t equals h.
Yeah.
So we will then go back to the main recording. And so we see that we want t to be h, and that's going to be the largest value that we'll take on. So we want to solve for a, h, and d. So I'm going to pause. I'm going to give you 10 plus 48t minus 4.9t squared, and I want you to find what a, h, and d are. So we're going to pause it right now, and I'll give you a chance one. Welcome back. So we're going to try to find the a, the h, and the d. And so the way we do it is we have negative 4.9t squared plus 48t plus 10 equals negative 4.9 t squared minus 99.6t plus 10. So how was that done? Well, one way of doing this was completing the square. And so basically just kind of knowing what to put in. This doesn't look so easy to follow. So how are we doing this? Well, what we did is we factored out the negative 4.9, and then we got 48 over negative 4.9. So I just approximated that as 99.6. It's a little bit off. And then we wanted to have the square, so we added and subtracted basically as we did for the quadratic formula. You can do it this way. It's not my favorite. My assistant did it a little while ago. We wanted to equal, a t minus h squared plus d. It's pretty clear that a has to be negative 4.9 so that the t squareds match. And so if we expand this out and set this equal to negative 4.9 t squared plus 10, we get negative 4.9 t squared minus 2ht plus h squared. What did we use to expand out t minus h squared? We used
the 48.
How do we expand t minus h squared? What's your rule to?
The inside outside.
Yeah,
FOIL.
first outside, inside, last. We use FOIL. And so as we go through that, we get, you could have had that as a and just have a equals negative 4.9. But then we match the t terms. And we have 9.8h has to equal 488. So 9.8h equals 48, so we can get what h is. And then we get d minus 4.9h squared. Oops, there shouldn't be a plus d there. Should equal 10. And so when we solve, we get them all. So again, what are we doing? Going back to so we have a minus h squared plus t equals negative 4.9 t squared. Was it plus 48? 88t. When we expand over here, we have t squared minus 2ht plus h squared d, and that still equals this. So when we expand, we have a t squared minus 2ht plus ah squared plus d. We put this in parentheses. The only way these can be equal for all values of t is if the t squared terms are equal. So we get a equals negative 4.9. And then we get negative 2h equals 488. I'm sorry, this should have an a here. So negative 2ah. So h equals 488 divided by negative 2a. And then finally, we have ah. So d equals 10 minus a h. Since we know what a and h are, we now know what d is. So we can keep solving one after the other after the other. So we're using our knowledge of quadratics to solve equations like this, to plot them. So now we can write the cannonball equation in a much better way. And so if we write it, where do we have it nicely written? Like this, negative 4.9 t minus 49.8 squared plus 10. What value of t is going to make this as large as possible?
49.8.
Yeah, because this quantity here is never negative. It's going to be positive most of the time. But it will be 0 if t equals 49.8. So when t equals 49.8, that's going to give us the maximum height.
Which is about what we
Yeah,
thought.
that's really close to 50. So looking at the curve, we did a pretty good job. How would you figure out where this hits the ground? What should the value of this function be when it hits the ground?
What should it be, like 1 or something?
Well, no, what's the value?
It has to be positive.
Well, this is the height. F of t is the height at time t.
Yeah.
What do you want the height to be when it hits the ground?
0.
0. So instead of using this equation, we might actually just use the quadratic formula and just use this equation and just set this equal to 0, right?
Yeah.
So if you do that, you would find when that hits the ground. So I'll leave that as an exercise to you to figure out when it hits the ground. All right, so you can now apply this to the path of a baseball. So according to physics, you would get the following. So imagine you shoot the ball at an angle, hit the ball at an angle, and then we'll have the cosines and the sines, and we've talked about these in one of the other lectures. I'm going to kind of gloss over that for now, but you get these nice parabolas, and so the height is going to be a parabola. It's going to as a function of time. H is the initial height, the height of the batter, the height where the bat hits the ball, and then V is the initial speed, and then you're going to multiply by the sine of the angle, and then you're going to multiply by time, and then this is using units of feet per second, so we're going to multiply t squared by 16, and that's going to be negative. The force of gravity is slowing things down, it's pulling things down. And then the horizontal component, we're assuming no friction, no air resistance, is just the initial speed times the cosine of the angle times the time.
What about with air resistance?
So that's a great question. Then it becomes more complicated.
Is there still like something for that?
There is still equations for those, but those are a little bit more involved. So over here, if we want to figure out the horizontal distance, how far the ball goes from home plate, what do we need to figure out?
Where it ends up.
Where it ends up at. So this tells us the y height, and this tells us the x distance.
Yeah.
To get the furthest x distance, what's true about the y height?
It has to be higher.
Well, what's the y height when the x height is the
0.
furthest? It's 0. So how would we figure out when the y height is 0?
Why don't we use the quadratic formula?
So we would use the quadratic formula to solve when does this equal 0, and then that would give us a time. And once we know that time, how would we figure out how far it went horizontally?
We would do we would solve for that.
Yeah, we would just plug in for the time.
Yeah.
So let's say the ball is hit at 176 feet per second at a 45-degree angle, and it's hit 6 feet above ground. So we can write down our vertical function as a function of time, and a horizontal function as a function of time. And then the time of flight, as you said correctly, it happens when the vertical height is 0. So we need to solve negative 16t squared plus 124t plus 6 equals 0. So we use our quadratic formula.
Yeah.
And when the dust settles and you simplify some of the algebra, you get the following. So the one we're going to want, do you think it's going to be the plus or the minus for the sign?
Plus.
Yeah. What do you think the minus sign might be?
Negative.
Yeah, but
0.
when do you think the height of the ball might be very close to 0? Not just when the ends and it hits the ground, but also
when the ball is being pitched, when the ball is being hit.
Right. Now, when the ball is hit, it's hit at 6 feet up. If you could go backwards in time a little bit, if it's a parabola, this would be starting it off before the ball coming out of the ground. Physically, does the ball come out of the ground?
No.
No. But that's kind of what it's like. Now, what's 30 squared?
30 squared?
Yeah.
Wouldn't that just be like 900?
900. 31 squared would be a little bit more than 960. It would be like 961. And so you can see that if we subtract off the square root of 985, we have approximately 0.
Yeah.
And so it's saying that the two places when the height is 0 is essentially about 7.8 seconds after we hit it, and a little bit before we hit it. And so these are reasonable. Now, at the end of the day, you get 967 feet. Do you think that's reasonable for how far the ball went?
No.
No, why not?
Because somebody probably would have caught it. It's only 6 feet in the air.
Well, no, but I'm saying This is how far horizontally the ball went, 967 feet on its whole path. Do you think batters are hitting the ball
No.
900? How about how far do you think the best home runs are?
Maybe like a little over 500 feet.
Yeah.
600?
So do you think the air resistance and friction is important? Yeah. And so it seems high, and we've assumed that there's no air resistance. So I did a little searching online, and on this website, which I encourage you to go to, it talks about projectiles and air resistance. And here, the nice blue curve is what happens when there's no air resistance, and the red curve is what happens when you do take into account air resistance. So as a nice exercise, and this is just barely doable, I think, with what you guys know, is let's try to figure out what is the best angle to hit it at. And so it turns out that the formulas from physics tell us that the vertical height as a function of time is 6 plus 176 sine of theta t minus 16t squared, where sine of theta is the angle that the ball is hit, and the horizontal distance is 176 cosine theta t. And if you haven't really seen sines and cosines before, these are the sides of a right triangle, so the sum of their squares is 1. Cosine of theta is going to go from 0 to 1. We could actually write sine of theta in terms of the square root of 1 minus cosine squared theta. So my question is, what is the best angle to hit it at to make the ball go as far as possible? So I will just say one thing and then I will let you guess. Now what's nice is this is a quadratic. Can we find the time as a function of the angle?
Yeah.
Yeah, that just changes which coefficient. Does it change A, B, or C?
Wait, C? Wait, what was it?
So as you change the angle, does that change the coefficient A, B, or C?
A.
Well, in our parabola, is the coefficient of A the coefficient of t squared, of t, or the constant term?
Constant? What?
For parabola, do we do it as, what's the coefficient of, say, x squared or t squared? We've been calling that
A.
And the coefficient of x or t we've been calling
B.
And the coefficient of the constant term. So when you look at this, what is A in this equation?
6? No. 16.
No.
Negative 16.
Negative 16.
Sorry.
What's B?
B would be 176
Sine theta. And what would C be?
6.
So as we change the angle, are we changing A?
Yeah. Right. Yeah, because
As we look at the equation,
no, we're changing.
are we changing B?
Yeah.
Yes, because the sign of the angle is changing. As we change the angle, are we changing the constant term? So what you could do is you could actually write down the quadratic formula and you could find the root in terms of this angle, and then you plug that time in here, and that would give you the distance. And you could actually plot that, and you could see which angle gives you the best. And again, you don't need to really know all of trigonometry to do this. You just need to know that the sine of theta is the square root of 1 minus cosine squared theta, and you could plot this. Do you have any guess between 0 and 90 degrees, which angle gives you the greatest distance?
Yeah.
What would you guess?
45.
And 45 is correct, at least if there's no air resistance. So that finishes today's lecture. Tomorrow's lecture, we're going to do another application. We're going to talk about the quadratic equation, the quadratic formula, and the Fibonacci numbers. And then in the lecture after that, we are going to talk about applications of the quadratic formula and the Fibonacci numbers to gambling. So we hope you enjoyed today's lecture. If you have any questions, feel free to email me. Be sensible,